So good morning, everybody. Welcome back. Today is Thursday, March the 4th, and we're going to go on our lesson on transformations of functions. But before we even do transformations of functions, we have to learn the 5 base functions. And these 5 are as follows. I'm going to give you the name. Unfortunately, I'm off screen if you're recording or hearing me. The first one is called the quadratic function. The second one is called the root function. I think it says radical function, but I like calling it root function. It's shorter, right? It's easier. Root function, square root function. The third one is called cubic. And again, it might not be in the order of your handout. The fourth one is called absolute. We'll talk more about that in a moment. And the last one is called reciprocal. And so these are the names. And what we're going to do is try to figure out what these functions look like. And so what we're going to do is a table of values. And that's why on your handout, many of you will be able to see it with no problem. And I am going to show on the graph what they look like. So for the quadratic one, I know there's more data than necessary, but a lot of you know what I'm going to do. For the quadratic one, I think you understand. We're going to input -3, -2, -1, 0, 1, 2 into that function. So it's relatively easy, right? Now, if you have to use a calculator, be okay. But a lot of you actually understand that the answer is going to be 9, 4, 1, 0, 1, 4. And so what does this parabola look like? What does quadratic look like? Well, sketch out the critical key points. I'm going to use blue chalk, that's okay. 2, 4, maybe even 3 and 9. So 9 is 6, 7, 8, 9. So something like that. So it looks something like this. And that's a parabola. Now you've learned actually how to graph the base or standard parabola. So if you need to pause the video or zoom in, please be my guest. But this is clearly y equals x squared. Really easy, because it's related to what you've done. So a lot of you, unfortunately, kind of memorize this. What's the vertex? Well, the vertex is 0, 0. That's a key point. It tends to open up. And it looks normal, right? Any question about quadratics? Really easy, right? Really easy. How about the second one? Notice what I'm going to do. I like doing it a little differently than the handout. It's the root function or radical function. Again, I'm off screen here maybe. Well, watch what I'm going to do. I'm going to use almost basically the same numbers. And there's a reason. So for the second one, right? This is y equals the square root of x. So we input the x values. Notice what we get. For some reason, the root function, there's no answer. A lot of you understand this because you just did the test. The roots are complex. 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 So there's no answer there. I can't even write 0. It's no answer, right? Everyone agree? There's no real answer. When you plug in -3, -2 into this function, there's no answer. It's complex. How about 0? The square root is 0. Any volunteer from the class? Omar. 0. Way to go. It is 0. The square root of 1. No pressure. Mackenzie? 1. The square root of 2. You might need a calculator for this. Can someone help out Mr. Chen? The square root of 2? 1.44. Who cares, right? Mr. Chen clearly understands. A lot of you think, Mr. Chen, this point is not nice, right? How about the square root of 3? Different volunteer. Omar can't do all this. Mackenzie?
1.73.
1.73. Keep going. Again, these two are not nice. Square root of 4?
2.
Nice. Square root of 2. Square root of 9? 3. So some of you say, Mr. Chen, what's this idea about key points or critical points? So in orange, and again, I might be off screen, but 0, 0 is a key point. 1, 1 is a key point. 4, 2 is a key point. 9, 3 is a key point. Now, I apologize, I'm going to leave this quadratic up, but if you want to see a fresh graph, please leave it there. Hopefully, I'm not confusing you. I will erase it in between so that you see fresh graphs. What does the root function look like? 0, 0, 1, 1, 4, 2, 9, 3. And that's what the graph looks like. For some of you that are in class, and I'll just sketch it out here. Here's a sketch that looks a little better. I'll try to get out of the way. That's what it looks like. Notice some differences in similarity to the quadratic. What's similar? 0, 0 seems to be key. What's different though? The parabola, the blue graph, it branches up positive in this direction, so there's some key features, right? So it kind of opens up. So for the root function, we can't really describe that, but clearly some of you actually understand. The domain for this orange graph, the root function, x is greater than or equal to 0 because it goes more and more positive. Can someone please help us with the range? What's the range for this now that you can see it? Omar.
Greater than or equal to 0.
Sorry?
Greater than or equal to 0.
Well, what? What is greater than or equal to 0? Thanks, man. I need to, some students are finding it difficult to remember what x's and y's are related to domain and range. Thanks, Omar. So y is greater than or equal to 0. If you're still not too sure, what's the domain for quadratics? The domain for quadratics, x belongs to all real numbers. What's the range? Y is greater than or equal to 0. So there's some commonalities. Let's just get it out of the air. Some students are noticing, Mr. Chen, if I tilt my head sideways, and this is actually wrong, so don't say that, the root function looks like a sideways parabola. Please never say that to me. That's actually wrong. That's wrong. There's no sideways parabolas. But in some sense, it kind of does. Everyone agree? Kind of does. That is incorrect. There's a reason why, because I don't want people to think that this is a quadratic. It's not. Quadratic either open up or they open down. Everyone okay so far? Am I going too fast? I'm going to erase this, and let's see if the class can help me out with the third one. Can it okay if I erase this too? Because I have to generate the graph again. And hopefully someone in class will fill this out for the cubic. The cubic. And as I erase, hopefully, you'll see what we're going to do. And some of you are slowly understanding, given the functions, what do these look like? Right? What does this look like? Oops. Oh. Try again. Hopefully the class will have this done. I redraw this so it's a little bit cleaner. And that's why I think on a graph paper it's easier. 1, 2, 3, 4, 5. 5. Anyone else want to help out, Mr. Chan? If you get it wrong, then who cares? Genevieve?
Negative 27.
Want to keep on going?
Sure. Negative 8. Negative 1. And then negative 0.125.
For 0?
Oh, sorry. For 0, it's 0.
Okay.
Sorry. It's 0. Oh, shoot.
That's okay.
Then it's 1. And then 8. And 27.
Nice, way to go. It's okay, don't worry. Relax, breathe, it's okay. And again, if you ever forget this, ladies and gentlemen, I think a lot of you know you can generate it, right? Basically, again, nicely done, for example, when x is negative 2, and you cube it, that's not right. Yeah, that's right, that's right. I'm stupid. Got this whole part. Negative 2 cubed is negative 8, that's nice. I'm glad you didn't say negative 6, okay? Because that's what I get as a comment. Anyways, let's use orange chalk if that's okay. Watch what I'm going to do. So 0, 0 is easy. Negative 1, negative 1, 1, 1, negative 2, and negative 8. Oh my gosh. So I'm not going to finish this all in. And 2 and 8. What's up here? So what does this cubic look like? Now, I kind of missed because I'm doing chapter. So I usually exaggerate it, ladies and gentlemen, as a sketch, and it looks something like this. This is our first exposure to cubics, higher order of polynomials. So they look kind of different. But notice what it looks like. I'm going to jump to class, hopefully I'm not on screen because it's embarrassing. This is what the cubic looks like. Looks like this. Not this. I didn't do this one. this. The negative one is down here, my right hand, which is what a lot of you are seeing to your left. And the positive part is up here. See what happens there? Right down on YouTube. Terrible. That's the cubic. Not always, but this is your first glance. So how would you describe this one? Well, any interesting features? I think all of these, what Genevieve said, and if you were hearing from the class, all of these are nice critical points. So all 5 of these are pretty good, right? And you kind of trace it through, and it looks like that. And I'm going to use an old phrase that Mr. Petal uses. He calls this like the squiggle. It looks like a squiggle because it actually cuts through 0, 0. Okay, so it's not a vertex. Oh,